Assalamu alaikum. Welcome to lecture. Welcome to lecture 19 of natural language processing. So today we will discuss another popular application of sequence modeling, which is named entity recognition. And we will be introducing this task briefly. And as you will see, this is very similar to the POS tagging task that we had introduced earlier on. So after the introduction of this task, we will then start with more general models for sequence modeling. And in particular, we will be discussing or starting the discussion for sequence modeling using neural networks. So we will be discussing recurrent neural networks starting today, and then later on we'll talk about GRU, LSTM, and then also transformers later on. So sequence modeling is essential in almost all NLP tasks, because as you know, NLP is a sequence of words or sequence of subwords or sequence of even characters. And most problems in NLP can be posed as a particular form of sequence modeling. And so as such, we do need a powerful sequence modeling tool. We had already studied one tool, which is probabilistic sequence modeling. And in that particular domain, we specifically talked about the hidden Markov model, which made some assumptions. But now we'll move on to neural network-based sequence modeling, which are more common nowadays. And they have kind of replaced almost entirely probabilistic sequence modeling, which was more popular till about 2010. So since 2010, neural network-based sequence models have become the dominant modeling approach for NLP. So I think so that's the agenda for today. We have a quiz at the end of class today as well. So I will start with an introduction to the named entity recognition problem, and then we'll move on to the general setting for sequence modeling. So named entity recognition is a specific form of information extraction. So information extraction is a general category of task in which, of course, as the name suggests, the idea is to extract the relevant pieces of information from large amounts of data. And in the context of NLP, information extraction could be anything relevant from text. And one particular piece of information that is of interest in many applications is named entity. So actually the named entity is not very intuitive, although when we discuss, I'll discuss some examples, it will become more clearer. So the idea of named entity recognition is we would like to identify names of entities or sequence of words that represent entities in running text. So I would change this to so sequence of words that are entities in running text. So entities can be of different types. So, and the type of entity that you're trying to identify is what is called named entity. So we are naming the type of the entity. So that's where you can say the name comes from. So what are the various types of entities that might be of interest? So it could be names of, for example, people. So this is the entity, person. It could be organizations, for example. It could also be locations. And it could be many other things, but these are the three main categories of entities that we may be interested in when we are talking about the NER problem, but there might be many others. In fact, the idea of named entity has been extended to numerous entities. For example, you can even have, so in general, you can have finer grained entities. So for example, you can even have dates, for example. So you can even have business names. So not just organization, but business names, or you can even think of cities. You can even think of countries, not just location, but finer granularity of location, cities, countries, uh, and of course, you can have other named entities as well. So let's say our goal is to find all names of persons in running text. Okay, so let's say this is our goal, and then let's say we are given some running text. Uh, uh, so for example, Asif, all right. So let's say this is running text. So from this running text, or given this sequence of words, we would like to identify where the names of people occur. So, so in other words, I would like to classify this sequence of words. So the answer would be something like this. Asif, let's say this is yes. So is, this is no. Sorry. What was the word? Attended, okay. So attended / no, hi / no, and so on. So we will like to label each word in the sequence with the appropriate tag, which says that yes, this is a named entity, in this particular case, the name of a person. Okay. But obviously names usually can be, named entities can be multi-word. So for example, Asif Khan attended LGS. So here, of course, Asif is yes, and Khan is also yes. Right? So one question that arises in such scenarios is that, is Asif one entity and Khan another entity, or Asif and Khan are the same entities? So it is possible that you may have two entities together. Uh, it is possible, off the head right now, I can't think of a example, but let's say if you have two different types of entities, for example, person and city, or person and location, maybe those two could occur side by side. So, so usually we would like a much richer way of tagging named entities. Remember, POS tag was just one word. Here, named entity in general can be multi-word. So we will usually use a slightly richer form of tagging, which we call the IOB encoding or tagging. So what does IOB stands for? Inside, outside, and then beginning. So in the case of the sentence that I wrote just now, so Asif, so this is actually the beginning of the named entity, and Khan, this is actually the inside of the named entity, which basically then implies that an entity that has started as B is continuing when you see an I there. And then we have attended. This will be outside. This is not a named entity. LGS. This is also O. So in other words, instead of just one label, we have now three labels, possible labels. Of course, for one named entity type, like the name of a person, we have three possible labels. Either it is going to be an I or O or a B. B means that named entity starts at that word. I would mean that the named entity is continuing. And then, of course, if it is not a named entity of that type, then it is O. So, for example, you have another. So, for example, you have Lahore University of Sciences is located in Pakistan. Okay. So let's say now we are tagging organizations. Okay. So then this would be Lahore. This would be beginning. University. This would be I. Of. This is again I. So the same entity is continuing. Management. This is again I. Sciences. This is again I. Is. This is of course O. In. This is of course O. And Pakistan. This is of course O. So using this tagging, you can get the complete entity or extract the complete entity from the running text. Okay, so that's the tagging for appropriate for named entity recognition. So once you have done this transformation or this encoding, your problem then essentially becomes a sequence labeling problem. You have an input sequence, which is sequence of words, and you have an output sequence of the same length, which is a sequence of tags. And the tags for one named entity type is 3, I, O, or B. Okay. So given labeled data set, you can learn a model, and once that model is learned, uh, you can solve likelihood, decoding, and of course, you can solve likelihood and decoding problems. Okay, using the HMM approach that we studied earlier in the previous lecture. Okay, is this point clear? So with this encoding, it essentially becomes very similar to POS tagging or sequence labeling problem, which is basically a sequence labeling problem or a decoding problem. Given running text, I want to get the labels from the appropriate set of labels. So if we relate it with HMM, so V is the basically vocab of all words, okay? And N, or sorry, S is a set of labels, so which is I, O, and B. And then of course, the size of S would be 3 in this case, and the size of V is, of course, the vocab size. And then you have lambda, A and B, which is the state transition probability matrix and the emission probability matrix. If you have both of these matrices, you can solve the decoding problem or the sequence labeling problem and do NER on your data set. Okay, a quick note about evaluation, and then I think I'll move on. So obviously you're labeling at every word level. Okay? So for example, Lahore University of Management Sciences, you're labeling every word. So you can do evaluation. So you can use, you can perform evaluation at word level, which is, you can say, intuitive because we are doing sequence labeling and we are labeling each word. And this is, of course, the same. So POS tagging also has word level evaluation. So you can compute accuracy, you can compute precision, recall, F1 measure, and so on. But sometimes in NER problem, we will also like to do evaluation at entity level, because that is gives you a clearer picture of how many entities the model has correctly identified. So for example, let me go back to my example. Let's say we have Lahore B, let's say, and university, let's say I, then we have of, let's say, O, and let's say management, let's say B, and sciences. So let's say your model did the following labeling. So Lahore is B, and then university is I, which means that the entity that it has extracted is Lahore University only. Off is not, it's outside the entity. Then management science is another entity. So if you do word level evaluation, of course, Lahore is correctly identified, university is correctly identified, off is incorrectly identified, management is also incorrectly identified. Management should be I. So management now is B. And then, of course, sciences is also correctly identified because it is I. So this will be word level evaluation. But it doesn't give you a clearer picture of how many entities the algorithm has clearly identified. In this particular case, you see that it has not identified the entity Lahore University of Management Sciences. The entity is the full sequence of words. So it has broken down it into multiple entities. The first two words are one entity, the last two words are another entity. So in essence, it has not identified this entity. So we will say that if you are doing entity level evaluation, then this entity is not identified. Okay. So usually in NER, we will provide both ways of evaluation because both of them are insightful and helpful in evaluating NER models. All right. Any questions? All right. So, so this is named entity recognition. Of course, if you have the label data set, you can train a model for multiple named entities at the same time. So let's say you have a model for detecting organizations and persons, and let's say locations all in one. So in this case, then the label set would be much larger. For each of those named entities, you will have IOB. So to distinguish that, maybe you can have the label set like this. For the first three are for organizations. So you can say B/org, then I/org, then of course O would be O, so I would not write that. So, and then we have दूसरा था person. Okay, then B/person, then I/person, and then we have B/location, and then I/location, and then of course O. So then this would be the tag set if you're doing multiple named entities in the same model. So you will have multiple tags. So you will have a B and I for each of those named entities. So again, if I take the example, so Asif attended LGS. So here, of course, Asif is, what is it? Asif is beginning of a person, right? And then attended, of course, is O, okay? And then LGS is, of course, beginning of ORG, okay? But again, it still remains a sequence labeling problem. The label set has been increased. And of course, assuming that you have the necessary training data from which you have learned this model. If you're using HMM, you have learned the A and B. All right, so I think with that, we will conclude this section. Any questions? So now let's move on to sequence modeling in a more general sense. And of course, this would be the precursor to the introduction to sequence modeling for neural networks, using neural networks. So in general, sequence modeling problems can be of four to five types. So let's discuss those types. Okay, first of all, let me introduce briefly the notation, and we will be using this notation throughout the discussion of sequence modeling with neural networks. So let's say we have an input sequence X. So this is an input sequence. And Y is the output sequence. So X and Y are sequences. And for sequences, we will use the angle brackets in the superscript to denote the position of the sequence. So so for example, I live in Lahore is basically, let's say, X. Just hold on, I would explain the notation in a bit more detail. So now X superscript 1 is the first position of this sequence. This is, of course, I. And X superscript 2 is the second position of this sequence, which is LIVE, and so on. So we will use this superscript in angle brackets, and the number inside the angle bracket denotes the position of the word that we are talking about. So as we have seen earlier on, X, as I said, let's say we're talking about 1. This is the representation for the first position word in the sequence. And usually this representation is a vector. So let's say if it is embedding, then this is the embedding for the word I. Okay. So if we are going to write the whole sequence, I will just write it as X. If I want to identify a specific word in that sequence, I will show it in angle bracket, the position. And of course, X if is usually a vector representation of that linguistic unit, word or sentence or sequence. And usually, if you write it in the strictest sense, it will be bolded. But while I'm doing it in class, I may not bold all X's or Y's, but you should understand from the context, it is a representation. And if that representation is a vector, then generally we will write it as X bolded. So now given this, our data set would be a sequence Xi and corresponding sequence Yi. And I, of course, is 1 to n. So we have an input sequence, we have an output sequence. So output sequence Y and input sequence X. So underline I means a subscript, right? So I oftentimes use the LaTeX notation. So, but sometimes it is quite intuitive. The underscore usually means subscript. All right. So now let's look at some sequence modeling problems. So categories of problems, you can say. So in the first case, what is known as many to many. So in this case, X is a sequence and Y is a sequence. All right. So of course, we have already seen examples of this. So Pierce tagging, X is a sequence, which is a sequence of words. Y is a sequence, which is a sequence of tags. And also NER, X is a sequence of words. And then, of course, Y is a sequence of labels. Okay. And let's say even, for example, speech recognition. So X is a sequence of words, you can say emitted or spoken by a person, and Y is a sequence of the transcribed word or transcribed words of that person. Okay? So that would be speech recognition. So in all of these examples, the length of the input sequence and the length of the output sequence is the same. But in many to many, you can also have scenarios in which the input and output sequences are not of the same length. So examples when sequences are not of same length. So can someone think of some example? So for example, machine translation. So machine translation. So let's say you have some sequence of words in one language, which is input, and Y is the output, which is a sequence of words translated in the other language. So the number of words in the two languages may be different. Maybe X is smaller, maybe Y is larger, or it could be vice versa. So machine translation would be this example. What else? So you can even have, for example, summary generation. So input X is, let's say, a whole passage, a news article, for example. Output Y is a summary of that news article. In this case, X is generally a longer sequence than Y. Okay? You can also have like paraphrase generation. So you have a sentence and which is X, and then you want to paraphrase that sentence, rewrite that sentence such that its content, its meaning is conveyed, but maybe in different words, that would be Y. Again, the number of words in X and number of words in Y may be different. Okay? And also in general, whenever you have generation, usually you will have X and Y of different lengths. For example, question answering or slash, you can say chatbots. So what do you have in a chatbot? You have one input sentence, which is the question, and then they have output sentence or sequence of words, which is the answer to that. So input sequence of words, the number of input sequence of words would be different from the number of output sequence of words. All right. So from these examples, you have noticed one thing. So we have covered almost a large segment of application NLP. So that's why we say that sequence modeling is so powerful. So many of our applications are essentially sequence modeling. And actually, you can think of other applications as well. So we'll come back to this category again. Now let's look at some other categories. So let's say you have many to one, which is what? By the way, let me introduce the notation. So since the number of words in X may be different from the number of words in Y, we use the notation T underscore X. So this is the length of sequence X, and T underscore Y to length of sequence Y. And of course, T underscore X can be equal to T underscore Y for, let's say, POS tagging, NER, and so on. But for others, it would be different. So in general, they would be different. So now many to one, so meaning that input X is a sequence, Y is a scalar or a vector. It's not a sequence. Okay? So actually, in this case, any text classification problem is essentially a many to one sequence modeling problem. So for example, sentiment classification or topic classification. So the input is a sequence of words. The output is a label from a possible set of labels, like say topics, politics, sports, and so on. So this is again sequence modeling. Why? Because the input is a sequence. Okay. And then we have another setting, which is called one to many. In this case, X is a scalar, comma, vector, or it could even be null, for example, nothing. Y is a sequence. So again, since sequence is involved, this is again sequence modeling. But of course, there is no sequence in the input. So one example that is commonly given in this category, although that's not strictly NLP, but it's sequence modeling, you can think of music generation. So maybe your input is maybe a vector describing the type of music that you want. Once you have given that input, your model would then generate uh, music as a sequence of symbols, music symbols. You can even think of this as, okay, so that's music generation. But you can also have a related problem from NLP, like, for example, auto generation of, let's say, uh, content. So X might be a vector that describes that I want a passage on, let's say, uh, a biographical passage on some person, let's say some cricketer, let's say Babar Azam, for example. So that is an input, and of course that's a vector. Just telling him that I want a passage on Babar Azam, the output, of course, would be a complete passage, which is a sequence of words. Okay? So other examples that are more closer to NLP are, for example, caption generation. So you have an image, which is some X, a vector, 1D vector or 2D vector, an image. And for that image, you want to generate a caption. What is a caption? A sequence of words that describes what is happening in the image. So that is image captioning. So that would be one to many. And similarly, you can have video subtitling and so on. So all of these examples are for one to many. And again, this is a sequence modeling problem. So we have so far discussed three major categories of sequence modeling: many to many, and within many to many, there are two scenarios. One scenario is input and output sequence are of the same length. The other scenario was input and output sequence were of different length. And then we have many to one, which is usually sequence classification or text classification, examples like sentiment classification. And then we have one to many, in which the output is a sequence, and we have examples like image captioning. And of course, if you want to complete this scenario, then you have one to one as well, but this is your standard neural network. For example, X is a vector, Y is a vector. So this is standard classification, you can say. So this is not a sequence modeling problem. Okay. So are these classifications clear? Okay. By the way, for many to many, another example is, of course, language modeling. So input is essentially text sequence. Output is also the same text sequence, but shifted one word to the right. So for example, I live in Lahore. So let's say this is X. So let's say this is Y. Okay. Okay. So this is the output that you desire. The input is what? The preceding word. So you have, for example, the start of sentence, then I, then live in, then Lahore. So this would be your X and that would be your Y. So this is language modeling. Many to many. So, okay, now with that, let's move to how we can use neural networks to do sequence modeling. So first of all, let's say if we have many to one. So input is text, output is a label. Um, so we were using standard neural network to do this. So how did we do this? We typically took a window of the input, and that window, for example, you took a window of input, and then of course represent that as a vector X, and then you have output Y, which is a class label for whatever problem you are talking about. Let's say it is sentiment classification, then this window is the entire text, and Y is the label for that text. Let's say positive class or negative class, or positive sentiment, negative sentiment. If it is, let's say, POS tagging, so then you would have done something like this. So I live in Lahore. So input X at any given point in time would be I live in, and Y would be the label for Lahore. So moving window, sliding window. So you're taking the three preceding words to predict the label for the next word. Then you move the window forward. So then next would be X would be live in Lahore, and Y so let's say you have an end of sentence also. Okay. So Y would then of course be the end of sentence tag. Okay. So you can use sliding windows to do that if you want to, but that's not an elegant solution. And one of the limitations of sliding window is you always have a fixed context, whatever you have defined. So in this case, we have defined a context of 3 words, and then you represented those 3 words as some vector. What would that vector be? So let's say that vector is, so let's say window of 3 words. Okay. So what would X be? So X would be, for example, a concatenation of embeddings of those 3 words. So let's say we have embeddings of size 300, then X would be so first 300 would be word I, next 300 would be word live, and then next 300 would be word in. So this would be the vector for X. And of course, I'm using embeddings here, but let's say if you had used one hot encoding, usually one hot encodings are sparse and the vectors are much larger. So they're not 300, they will be easily in the tens of thousands. So you can think of, let's say if it is 10,000, you would have a 30,000 long vector for just 3 words. In this case, you have, if you are using embeddings, you have 900 long vector for 3 words. So you will have a massive network neural network, if you're talking about neural networks, to process this. Another issue with doing this and using standard neural networks is, so again, looking at this representation X, X is a concatenation of embeddings or one-hot encoding. So, for example, so we have I live in, so this is, let's say 1X, let's say you say this is X1, and then live in Lahore, this is X2, right? Sliding window. So you notice that, so in X1, live appears, the embedding for live appears in the second position. While in X2, the embedding for live appears in the first position. And this would happen for all sentences. Any particular word may occur in any position of a vector, right? So the problem with that is a neural network would not then be able to understand properly that word, because, for example, if you think of a neural network, standard feed-forward neural network, we have W1, the weight matrix. So the first part of that matrix would be associated with I in the first X1, and in the second vector X2, live will be associated with the first part of the weight matrix Wi. So the weight matrix, first part of weight matrix Wi would thus be confused between I and live. Okay. So in other words, it will have a harder time trying to understand and distinguish between the different words, because those words' positions would be changing throughout your data set. So these are some of the limitations of using a standard non-sequential neural network for solving sequential problems. The first one was the context is fixed, and that is predefined. While, as we will see later on for sequential neural networks, the context is generally not fixed, and the neural network learns the context itself. So it could even go back hundreds of words theoretically. And secondly, the standard non-sequential neural networks may become very large because the input vector may become very large. And thirdly, they might be mixing of information because a particular word may occur in multiple positions, and neural network would become confused to properly represent that word. Of course, LIVE is the same word, but in one case it is appearing in the first position, in the second case appearing in the second position, and so on. It has to be then processed with different parts of the weight matrix W1. So these are some of the motivations for using sequential models. So this leads us to our first sequential model, which is our recurrent neural network, which is also called RNN. Okay. So recurrent neural networks, as the name suggests, is a neural network which can process information at different time steps by taking information from the previous time steps. And the best way to represent recurrent neural networks, this one as well as the future, is through equations. You can always draw some figures as well, but usually equations are a better way of understanding these networks. So let's understand this. So let's say you have a recurrent layer. So previously we had feed-forward layers. So let's say when we talked about multi-layer perceptron or feed-forward neural networks, we had multiple layers. So let's say two-layer network would have one hidden layer and one output layer. So the hidden layer is a feed-forward layer. Output layer, of course, would depend on your problem. It would be using softmax if it is multi-class classification and sigmoid if it is binary classification. So in this case, we are talking about a internal layer, which is a recurrent layer. So we call this a recurrent layer. Okay? Not a feed forward layer. So what happens? So let's take an example. Let's say we are taking a POS tagging example. Okay? So we have input sequence X. So I live in Lahore. Y would be I is what? I is pronoun, right? So let's say I pronoun. Live is verb. In is preposition. And Lahore is a noun. So both sequences, of course, are of the same length. So I live in Lahore is a sequence of words, and the second one is a sequence of labels or POS tags. So in a recurrent neural network, we will first be feeding in I. Of course, it's representation of I. So once this representation of I goes in, it is processed. So the information that is processed for I is then fed, is kept in some form in the network. And when next you feed in live, that information that is kept from the previous part also goes or added, it's added to live or live. So once you have added that information to the new information live, you get a new information, which then again is fed into the information for in, and so on. So in other words, there is always a vector that is containing information from previous iterations that is fed into words that you feed in at any particular point in time. So let's try this in terms of equations. And I will then briefly show you a simple diagram for it. So I will be using the notations which are somewhat similar to the book, but that are more identical to some notes or lectures by Andrew Ng. So I will share those videos as well. So Andrew Ng की एक series थी, I think some few years back, using sequence modeling for NLP, एक वो lecture post था. तो उसकी videos में जो notation use हो रही है, I'm following that more closely, although it is related to those in the book, but I'm going to follow that more closely. Okay, so वो videos मैं share कर दूंगा on LMS later on. So we are also running out of time, so I will probably write these equations and then start from it again. So what happens? So we have an activation A. So activation at time 1. ठीक है? So of course ये अब angle bracket superscript में होना चाहिए था. I have written it in. No, I have not written the superscript, but you should understand. And this activation, if it is a single unit, if it is a single unit in the recurrent layer, this will be a scalar. But in general, this would be a vector. A would be a vector, meaning that the recurrent layer would have multiple outputs, just like a feed-forward layer has multiple outputs. F, this is the activation function or transfer function. And then we have W, subscript AX, which is the weight matrix multiplied with the matrix X, input X time 1, plus we have another weight matrix, which we say WAA, which takes as input the previous output 0, plus of course B bias A. So this is the recurrent equation. If you relate it with the standard layer, feed forward layer, you did not have that part WAA multiplied by the vector AX0 from the previous iteration. That's the only difference. So in other words, जो previous time step में जो output A थी, वो next time step की computation के लिए use हो रही है. ठीक है? And then the output Y. So just to distinguish this output from the true value of Y, I will put a prime here. But sometimes I will not put a prime. You should understand कि ये network output and not the true value. 1 would then be some G, another activation function of another weight matrix Y A multiplied by A 1 plus B Y. Now this is a standard feed forward layer. Okay? And of course, this is the output layer. Okay? So at every time step, you have an output Y. So you inputted X and then you outputted Y. So later on, actually, you will see that you can generalize this. You can have multiple recurrent layers in series, and you can also have multiple hidden layers before the output layer while making the prediction. So this generally is called a feed-forward layer, and that is called a recurrent layer. But let's say we have just one recurrent layer and one output layer. So what is the so let's say we started with we are doing the POS tagging problem. So X1 would be the representation for the word I, right? So what would A not be? This is actually the starting activation. So usually this is taken as all zeros because we don't have this. Okay. Unless you have some activation for the starting of a sentence, but usually it's taken as all zeros. So given this, you can compute A1 using that equation, which is F W AX into X1 plus W AA into A0 plus BA. Of course, here B and the two W's are the parameters of the recurrent layer. The parameters of the recurrent layer, and these would be estimated as part of the optimization problem. So I think I've introduced the basic equation. So in the next lecture, we'll start from here and discuss some applications of RNN, and then later on we will extend RNN to other models like GRU, LSTM, and then later on to transformers. So I'll be sharing the videos by Andrew NG as well on your LMS. So you can look at those as well. They are quite concise. But of course, all of this material is available in your textbook also. Please read the textbook also. It has slightly different notation, but it's still understandable. And next time I'll also explain how we got this WAA and WAX, what is the reasoning behind this. Of course, it's very similar to the notation that we introduced earlier for feed-forward networks. So वही notation है, but I'll just explain it again next time. ठीक है? Any questions? Any questions?